Welcome everyone to today's webinar. Before we get started, I just wanted to give you a few points about the logistics of Zoom. So today we have the chat feature. You can chat with hosts and panelists if you have any technical issues. If you have questions throughout Professor Mannering's presentation, please put those in the Q&A box. There's a Q&A icon at the bottom of your screen. You should be able to click that. It'll open a panel. You can type your questions there. You can see other people's questions. If you like questions, you can upvote them. At the end, if we have a lot of questions and we can't get to all of them, we'll prioritize based on the ones that have the most upvotes. And then we do have the raise hand feature available as well. So when we get to the Q&A time at the end of Professor Mannering's presentation and you'd like to verbally ask a question, you can click the raise hand feature. We will have the webinar recorded and it will be posted to PacTrans YouTube account probably within a day or two. And I think that's probably all you need to know. So with that, I'd like to welcome PacTrans Director, Professor Yinhai Wang, and he's going to do the introduction.
Thank you, Cole. Hello, everyone. Thanks for joining the PacTrans Winter Regional Webinar. We are so honored to have Professor Fred Mannering to join us as today's webinar speaker. I bet a lot of you know Professor Mannering. Let me share one slide with you. Professor Mannering was our department chair when I joined the University of Washington as a postdoc. Professor Mannering is currently executive director of the Center for Urban Transportation Research and the professor of civil engineering, civil and environmental engineering at the University of South Florida. He was also department head at Purdue University before he moved to University of South Florida. He's an internationally recognized researcher in transportation safety, but maybe very few of you know actually Professor Mannering is also a motorcycle racer. One more thing I want to let everyone know that Professor Mannering is also a musician. He's a great guitar player. This is actually his band. I actually look at his background and found all these things. So today, certainly our focus is Professor Mannering's talk about transportation safety, specifically on risk compensation and the effectiveness of vehicle safety features. But certainly he could have a lot of other things to cover. With that, I would like to welcome Professor Mannering for his webinar talk. Fred, now the floor is yours.
Thank you. And thank you for that talk. So for that introduction, let me share my screen. And we've tested this, so we should be able to get everything to work. And then we got one more switch here. Okay, I think everything looks good.
Yes.
Great. So again, thank you for the introduction. Yeah, it's unfortunate that I wasn't able to make it out to Seattle this spring, but hopefully I'll make it out in the fall. And because my heavy metal band was in Seattle and a lot of my racing was at Seattle International Raceway, which is now Pacific Raceways. But today, I'm going to talk about risk compensation and the effectiveness of vehicle safety features. And I'm going to present some data, which is actually from Washington State, but in the 1990s, I'm going to talk about airbag and anti-lock brake introductions in cars, and then try to extrapolate some of the findings from that research to the safety features that we have today. Now, these three figure illustrations here. The first one is actually my mother's car. My mother had so many, fortunately no injuries, but she had so many accidents. One time she had an accident. The insurance company gave her a rental car and she crashed the rental car. So, what are the odds? But the airbag, this is her Ford Escort. I think it was a mid-1990s Ford Escort, but the airbag's very effective. But today, safety features have gone well beyond airbags. So we have heads-up display. I don't know if any of you have ever driven a car with heads-up display, but it's amazing. Usually you have radars going out the side that pick up cars to your side. And then we have autonomous braking, all sorts of safety features. And the question that this presentation is going to ask and start thinking about and provide some empirical evidence is, do these safety features actually make us safer drivers? Or do these safety features actually make us faster and more distracted drivers? And so I'm going to give an argument for what we'll call risk compensation. So if you look, this is the interior. Actually, I have a Mazda CX-5. This is a Mazda CX-5 interior, and it has autonomous braking. So if you start getting close to the vehicle, it flashes brake, and before it actually does brake. Personally, I find when I'm starting to drive more aggressively, this autonomous feature is putting on my brakes and everything. It's a pain in the butt sometimes. If you're like, I can imagine if you're on a racetrack, it'd be very difficult. But you can imagine having all this safety features, knowing that the cars would stop by itself if you're not paying attention, might make you more likely to not pay attention. So let's look at what this means. So if we look at some accident fatality trends, if we look at the 10-year period, 2011 to 2020 inclusive, so 10 years, total fatalities actually rose over 19%. There were 32,479 in 2011 and 38,680 in 2020. And you have to ask yourself, with all of these safety features, even the fatalities per 100 million vehicle miles traveled, so you can't say, oh, people are driving more, so you expect them to go up. But even the fatality rate has gone up 25% over the same period. So you have to ask yourself, with all these safety features we have in cars, what is going on? So let's take a look at, what about safer cars? If we look back, given the significant advances in vehicle safety technologies over this 10-year period from 2011 to 2020, why has there not been a decline in fatalities? And why have accident rates not declined in a significant way? So you'd expect, well, maybe there's more driving, so maybe the fatalities would creep up, but certainly fatality rates should go down. So when we look at the effectiveness of safety features, a lot of people that analyze safety feature effectiveness, and I'll show you a quick video in a few minutes, often justify their effectiveness based on initial data. So they do comparisons of accident injuries in cars with and without the safety features. But the problem with doing that is that people that buy safety features in cars are usually the safest drivers. So if you look at the effectiveness of a safety feature in a car, it's going to look really effective at first because the safest drivers buy the safety features in the cars because they really have a high priority on safety. And you're not going to know how truly effective the safety features are until everybody starts driving the cars, even the reckless drivers that are not driving cars initially with all these advanced safety features. So the problem with this initial comparison, as I've described, is assessing the effectiveness of vehicle safety features involves a non-random sampling problem. Now, this can be solved with some econometrics, but it's not an easy econometric fix. I'll talk about that in a few minutes. But the reason is, as I mentioned a few seconds ago, individuals that are first attracted to new safety innovations are a non-random, self-selected sample of safer drivers. So you can imagine if you put a spike in the middle of the steering wheel and said it was a safety feature, if the safest drivers started driving, you'd probably say the spike in the middle of the steering wheel is a very effective safety feature. Maybe that's a bad example because it probably would be a good safety feature because you'd be constantly aware that you could die at any minute. Wait, I got my, every time, since we're not having the interaction, I have a little thing for the jokes. So the considerations then is sample of safety feature adopters is not in non-random, once having safety features. So you have this non-random sample, and then once you have the safety features, their effectiveness may be offset by more aggressive driving. So we're going to address both of these considerations in this talk. So you have a non-random sample because people that get the safety features are the safest drivers. And then once the safest drivers get the safety feature, they may offset their behavior. And I'll talk about this in a second, but the general idea I'll throw out now is, let's say, and I'll repeat this a couple times as we go through and I start showing the graphs and equations. So let's say I like to have a 1 in 10,000 chance of getting into a car crash. That's what I feel I'm comfortable with. If you give me a safety feature that makes my chances of being injured in a car crash 1 in 20,000, then I'm going to say, well, I'm happy with 1 in 10,000. So I could drive faster, I could drive distracted, etc., to get down to the 1 in 10,000 chance again. And that is what I'm going to argue is what's probably going on with the safety features that we have in cars now, at least to some extent. So let's look at the background here. You can think of it as individual drivers face a trade-off between speed and safety. And it's really not just speed and safety, but it's other things in safety. So if I were to put safety features in cars and I could expect all of the benefits to come out of safety, or some of the benefits may be taken in speed, and not just speed, it could be distracted driving, right? Because as you're driving distracted, you could be, being productive. You could be listening to my webinar in the car, and you have all the safety features, so you wouldn't feel that your safety risk is increased incredibly. So the individual drivers facing this trade-off between safety and speed and distraction, other things, they reach an optimal speed safety trade-off by the type of vehicle they own. So if you have a high emphasis on safety, you're going to buy a car with a lot of safety features, and their driving behavior, because you can drive distracted, you could adhere to the speed limits, tailgate, have gap acceptance. Your driving behavior could also change. So these are going to be the ways you would adapt to safety features. So what can change the speed safety trade-off? So everybody has a speed safety trade-off. You get in a car, you establish what your speed safety trade-off is, but there could be technological changes to the vehicle, changes in the driver's skill set, as you age or you take high performance driving courses, that's going to change your equilibrium. Improvements in roadway design. We've made a lot of improvements in roadway design for safety purposes. Changes in traffic conditions, congested traffic, non-congested. Changes in drivers' risk-taking behavior. This could just change naturally over time or could vary at different points in your life. And then changes in driver distractions. For example, if we were analyzing the data from the 1990s, we weren't having cell phones and other distractions that we now have. So there have been changes in technologies there. So the motivation for this study and thinking about how people might risk compensate is the advances in vehicle technologies. Now, the data that I'm going to use from Washington State is going to look at airbags and anti-lock brakes. So these are some of the early big improvements. But since then, some of the other earlier ones are traction control, electronic stability control, adaptive cruise control, pre-collision systems, forward collision, lane departure, autonomous braking, blind spot detection, adaptive headlights. Now, I should tell you, I sort of collect cars, so I have 7 cars, and the oldest one I have is a 1969 that doesn't have any of these features. Actually, 1969 was the first year that required shoulder belts. So before then, you had a seat belt, but not a shoulder belt. Then I have a mid-90s car that just has the airbags, but no anti-lock brakes. And then I have an early 2000 car, it's a Mercedes, but it has electronic stability, everything up to the adaptive cruise control. And then I have one one car, that's the Mazda CX-5, that is everything, the adaptive headlights, everything. But I find myself, as I go from one decade of technology to another, I find it, you start getting used to, for example, the adaptive cruise control, and you go back to a car from the 2000s, and suddenly you're coming up on another car, and your car is not slowing down. It's like, well, oh, I'm in the wrong car. So, it's interesting how you can, how having different technology levels in your different cars could also affect how you drive and behave. So let's look back into the 1990s, because that's what the data is going to be, what I'm going to present, the offsetting behavior data. And what would we expect with anti-lock brakes and airbags? So these are like the earliest technologies, aside from, seat belts and shoulder belts. Anti-lock brakes, you would expect to reduce the frequency of crashes because you'd be able to stop before having an accident. And you'd reduce the severity of accidents once they occur because you'd have a lower collision speed, less energy would need to be dissipated. And then for airbags, that should reduce the severity of accidents once they occur. There might be some effect on the frequency of accidents, because if you know you have a car with airbags, it's, I can drive a little faster because I have a car with airbags. But you're not going to have the same effect on the frequency of crashes as anti-lock brakes would. So why haven't fatality rates declined dramatically? You could say, well, there have been changes in traffic conditions and laws, congestion, higher speed limits, right? A lot of speed limits have increased from the early 90s. Changes in vehicle fleet composition. You have very large SUVs. Even the light trucks are very big, and then you have small cars. You could say, well, maybe there's some, mass differences between vehicles that's causing a problem. And of course, there's changes in driving behavior with drivers driving faster and more distracted. But in addition to all these, I'm going to make the argument for risk compensation. And the idea here is that consumers respond to safety innovations by becoming less vigilant about safety. Now, if we look at the economic literature, there's a lot of aggregate economic work that has found evidence of offsetting behavior with seatbelts, very early safety features, and other safety devices. For example, there are seats for infants, bathing infants in the bathtub, and they found that once these parents have these seats for infants in the bathtub, they become less vigilant about watching their children, having bath in a bathtub. So it's not just with transportation, but there are other elements of household safety where this has been observed. So the question is, has this happened, and will it continue to happen with the new safety innovations that we are now going through? So I'm going to present a video from Good Morning America, which I did. This is probably, I think, like 2004, 2005, when our results first came, actually it was 2006, when our results first came out using the Washington State Airbag anti-lock brake study. So let's watch this video to see what Good Morning America has to say about this.
Thank you, Kate. So glad you were alert to that online information. And we have another study tip for you this morning. There is a new study out today that shows side impact airbags can reduce driver deaths by 37%. Adds up to thousands of people a year. But consumer correspondent Elizabeth Leamy has uncovered some provocative and controversial information. She joins us from Washington to explain about that. Elizabeth?
Diane, today's study focuses on the kind of side impact airbags that protect your head. But there's another study out that questions whether our basic human nature undercuts great safety features like that. This crash test video shows the results of brand new research. First, a collision with the type of side impact airbags that protect the head, and now without.
If all passenger vehicles had head-protecting side airbags for front seat occupants, we could save as many as 2,000 lives a year.
Just last month, the government announced it wants to save lives with mandatory electronic stability control in all cars. We tested the technology earlier this year at Consumer Reports. Watch how the car on the left, with the stability control on, automatically adjusts when the driver starts to lose control. But not so fast, says Purdue University engineering professor Fred Mannering, who points out auto fatality rates are going up. He co-authored a study that finds the safer we make cars, the worse we drive.
What we found is that people tend to compensate for advanced safety features such as anti-lock brakes, airbags, electronic stability packages by driving more aggressively.
In other words, if vehicles are safer, people may drive faster, take more risks, and that could mean more accidents.
If we could find some way to modify the human behavior, then these would be truly effective.
We've looked at drivers in vehicles with the safety device and drivers in vehicles without the safety device, still finding a major safety benefit.
What do drivers think?
I think we get the mindset that you're safe because you have all this technology around you, when actually it still takes common sense to be a good driver.
Obviously, nobody wants to stand in the way of progress, so new safety features are always welcome, but you also need to remind yourself to drive safely, Diane. By the way, those head-protecting side airbags will become standard in the year 2010.
That's right. Next safety tip, overcome your own instincts. Now time for the weather and Sam Champion.
Good morning, Diane. It may look like I'm ready for a thorough examination, but...
Okay, so let's go on and digest what was in that. The first thing is you'll notice the lady from the National Highway Traffic Safety Administration, or she did exactly what you're not supposed to do. Look at people with the airbags and people without the airbags still finding great benefits. That's exactly 100% incorrect. But that's what you would, if you weren't thinking about the problem, that's what you would do. And let's look at the Insurance Institute for Highway Safety. When they were evaluating the effectiveness of side impact airbags in 2004, they estimated they were 45% effective. So these are collisions, side impact collisions, the likelihood of reducing fatality, 45% in 2004, 37% in 2006, 31% in 2008. And presumably there were multiple years after that. So why is the effectiveness going down? Well, it's not because the airbags are becoming less effective. What's happening is the more reckless drivers are starting to get into the cars and causing more severe crashes, right? So the only way that you're going to know truly how effective the side impact airbags are is if everybody has a side impact airbag car. But that's not how we want to evaluate safety features. We want to come up with a way to estimate their effectiveness without having to give it to the entire population. So the problem, again, that drivers that first owned cars with side airbags were a non-random sample of the driving population, safer drivers. So what we need then to solve this problem is we need disaggregate data, which means individual data on what the types of cars vehicles own and how people drive, accident records, and so on. And we must account for the self-selectivity. So what types of consumers are most likely to switch to new safety devices? Then once they get to the switch and get the safety devices, will such consumers be more, less, or equally as likely to be accident involved after the switch to newer safety features? So we have the self-selectivity, and then we have the risk compensation. So if we look at the analytic framework, there's Sam Peltzman at the University of Chicago in 1975 estimated a paper where he suggested there's risk compensating behavior with people that use seatbelts. And then Skip Viscusi is another economist that wrote a similar paper in 1984. So what I'm going to do is I'm going to show you some graphs. I'll mention what's going to be on the graphs is that you have some utility maximizing driving where you're trading off safety and driving intensity. And driving intensity, I'll call speed, risk-taking, distracted driving. And there will be some marginal rate of transformation between these two. So let's graphically see what this looks like. So here you have a marginal rate of transformation. It's sort of like an economics utility curve. And there's some equilibrium point where you have your driving intensity, which would be how fast you want to drive or how distracted, and then your probability of avoiding an injury. So there's some equilibrium that gets set up. Now, what happens when you get a car with the safety features, then that shifts this capital S prime, small s prime curve to the right. So the assumption that is usually made is that you will drive with the same intensity, same speed and so on, and then you'll move to point B. So your probability of avoiding an injury will become larger. So you'll be less likely to be injured, a greater likelihood of avoiding an injury. Now, that you can think about it, there's a way, if you increase your speed or distracted driving to take all of the benefits of the safety features by additional intensity, then you would move to point C. So this is my idea that I presented at the beginning of the talk, where I said I like a 1 in 10,000 chance of being injured in a crash. So in that case, your probability of injury will be the same, and then you'll just be able to drive faster. So there's still benefits. You'll be able to get to work quicker, or you can answer emails and do all sorts of watch videos while you're driving. So there's benefits to that. But possibly there's this is a complete compensation so you take all the benefits in driving intensity, but more likely it's somewhere, you're going to end up somewhere between B and C. And there's also, and I'll talk about that, is you could severely overestimate the effectiveness of the safety features and end up at some point E, where you're actually even more dangerous than you were before you had the safety features in the car. So you could greatly overcompensate. Now, if this intensity, this driving intensity, is a normal good in economic terms, you would expect the consumption to be to the right of this point B. So at some point, it's unlikely that you would take all of the benefits out in pure safety, but it could range from B to C, or in an overconsumption alternative, you could end up at that point E. Now you have to remember that each person has their own equilibrium point, right? Because it's not an equilibrium point for the entire population. If you had a safety conscious driver, they would greatly value the probability of a driver avoiding injury. So their equilibrium point will be up here, and their BCs will be pretty close. If you have a high risk driver, you would be down here at point D, and then your compensating triangle would be much larger. So, but you have to think of everybody as you're driving this car, everybody's making this trade-off between speed and safety. Now, the way that I sort of developed an econometric or statistical model that addressed this is we have to look at the types of people that are going to buy cars and then their likelihood of getting into a crash. So I estimate a model that has the probability of an accident, the probability of owning a car with anti-lock brakes, and the probability of owning a car with an airbag. Now, I should tell you, when I give this talk to my econometrics class, we spend a lot more time on the details because this is a really cool econometric model. That selectivity problem, trying to determine what type, the self-selective sample, that the safest drivers own cars with airbags and anti-lock brakes first. That selectivity problem was actually first addressed by James Heckman at the University of Chicago, and he actually won the Nobel Prize in Economics in 2000 for his work on this. So this is an extension of that work, because we're going to look at, when he won the Nobel Prize for that, he had a binary choice. We're going to look at a multinomial choice. So we need to account for the contemporaneous correlation of error terms and the endogeneity of airbags and anti-lock brakes. So, and again, this becomes more of the econometrics part of the talk. I'm going to skip over this a little bit quickly, since this is not an econometrics class. But the accident outcomes will be no accident, a non-injury accident, or an injury accident. So we have 3 accident outcomes. And the data that were used, and maybe some of your parents were in this data, we have 1,307 Washington state drivers, and we monitored them from 1992 to 96. We have the socioeconomic information of their households, the vehicle data. And since we're going over this 5-year period, 92 to 96 inclusive, that's 5 years. There was one time I had a paper review, 96 minus 92 is 4 years. It's 5 years, it's inclusive. But so we have observations from these households over the 5-year period. And over that period, 271 households switched from non-airbag to airbag cars, 270 switched from non-ABS to ABS, and we observed 614 accidents over this 5-year period. And we linked it to Washington state data on all reported accidents, so we get the state reported data as well. So when we look at the econometrics or the statistical modeling, the modeling system has one trinomial model, which is the accident model. You have no accident, an accident, or an injury accident, a non-injury accident or an injury accident. And we have two binary models, whether you have a car with ABS or not, and whether you have an airbag car or not. So the trinomial accident model is coded as 3 binary variables with y equals 1 if the outcome I occurs and 0 otherwise. And the no accident outcome is used as the base. So without loss of generality, we have 4 binary variables, 2 for accident outcomes and 1 for the airbag and ABS choices. So graphically, this is what it looks like. And mathematically, so we have some function that determines your probabilities of getting into an accident and then owning a car with an airbag or anti-lock brakes. And econometrically, this works out that you have a cumulative 4-variate normal density function. So this is estimated with maximum likelihood estimation. I think in my undergraduate text, I think at the end of chapter 8, there's a little thing that talks about maximum likelihood estimation. But if you do my graduate text, there's whole chapters on this stuff. So we don't have a closed form solution when we maximize this likelihood function. So we have to use a numerical simulation, and we programmed this in Stata using 800 random draws. So we did not find great difference between 400 and 800 draws. So since you do not have a closed form of the integral to estimate the probabilities, you have to do numerical integration. And so we use random draws for that. And we also considered weighting our sample so that our sample was an exact replication of the Florida or the Washington state population at that time from 92 to 96. So quickly for the estimation detail, we considered random effects, the possibility that, the household, each individual had correlated observations for the 5 years. We considered random parameters. We considered possible misclassification of accident outcomes, and we did a likelihood ratio test that showed the error term correlation was significant among the equations. And if you really want to see the technical and estimation details of this paper, just send me an email and I'll send you a copy of the paper. So if you're interested in that, but we're going to look at what are the findings and then what do those findings mean for safety research. So for the accident model expectations, with no change in behavior, airbags should reduce injury accidents, right? So if there's no change in behavior, the airbag should reduce injury accidents. With no change in behavior, people aren't compensating. And so I mean by the change in behavior, ABS should decrease the accident frequency, and it should decrease, accident injuries. So the frequency of crashes and then also the injuries, because you're scrubbing off some more speed. So let's look at the model estimates. Now, some of the other factors, these are elements, variables that we wanted to test to see if they significantly affected your probability of having an accident. Now, the things that I point out, there's, whether you're a commuter, elderly, there's a bunch of variables, but the ones that we're most interested in is the airbag indicator. Does the car have an airbag? So the parameter estimate for that is 0.34 and the standard error is 0.277. So if, some of you have probably done t-statistics and so on, this is not significantly different from 0. And if we look at the ABS indicator, the mean of that variable is 0.088 and the standard deviation, standard error is 0.271. So even one standard deviation away, we cross 0. So for both of these variables, we can say they're not significantly different from 0, which means that airbags and anti-lock brakes are not significantly affecting the probability of having an accident. So the probability of having an accident with an injury, so that's an accident in general. Now the accident with an injury, we would expect both airbags and anti-lock brakes to decrease the probability of having an accident with the injury. And they are negative, and that's good, but the standard error is very large. So within one standard deviation, you're crossing zero. So once again, neither of these are statistically significant from zero. So the conclusion we can draw from this data is that airbags and anti-lock brakes are not affecting the probability of having an accident or probability of having an injury accident. So airbags and accident probabilities, the effect of the airbag is statistically insignificant in an injury accident, suggesting that they are ineffective or that drivers with airbags may be driving more aggressively. Now, I should mention, there's a little bit of an argument for the airbags being ineffective. It's not like everybody had Takata airbags back then. But there were airbags that when they first started out, they weren't nearly as reliable as they are today. And there were stories that some of the early airbags exploded so quickly you couldn't blink. So you would get abrasions on your eyes and things like that. So there was some argument about, how effective are they really? Do they launch? Okay, there's the speed at which they launch. So there was some argument about that, but most of it is we're arguing that drivers are more aggressive. But if you look, even back in the early 90s, Peterson, Hoffer, and Milner found that injury claims increased in vehicles following airbag adoption as a standard feature. So there's some evidence, some aggregate evidence of this compensating behavior. For anti-lock brakes, ABS should decrease accident frequency, both the accident probability of having an accident and the probability of having an injury accident. But anti-lock brakes had statistically insignificant impact on injury accidents, as the model estimation results I showed indicated. Allison Smiley in 2000 found that claims on ABS vehicles were higher for taxi drivers due to reduced headways when driving with ABS. And I also have sort of an anecdotal story. There was a few years back, the Florida State Highway Patrol, the motorcycle division of that, all went from regular motorcycle brakes to anti-lock brakes. The first year, there was a reduction in crashes, but the second year, the crashes were exactly the same level as they were in the first year, suggesting that some compensation is going on. Just, you can think about your personal experiences here. My personal experience, when I get into my, again, I have cars from the 1960s all the way up to the 2010s. When I get into a different car, within a matter of seconds, I start adjusting my driving behavior because my 1969 car doesn't brake anywhere near as well as my 2018 car. So you instantly have to make adjustments. And when you start noticing how quickly ABS can stop your car, it can change your behavior significantly. So what are the implications of these findings? The disaggregate findings we have based on these 1992 to 96 Washington State people corroborate some of those early 1990s findings. Drivers seem to have accrued benefits with greater mobility, driving faster or driving distracted, which is more relevant perhaps in today's environment. And then non-airbag and ABS owners may be at greater risk because of this offsetting behavior. So the idea here is that there's an equity implication here. If you have people with safety feature cars driving more recklessly, what that's going to choose is it's going to impose an externality on others. And we've noticed this looking at some accident data is that vulnerable road users, pedestrians, bicyclists, motorcyclists, their accident rates are really starting to go up. And one possible explanation for that is you have these maniacs driving around in cars with high safety features. Their risk is staying at 1 in 10,000, but they're imposing risk on others. And the same could be true if you have a car with an older technology, is that you can be absorbing the externality of these people that are offsetting their behavior by driving more recklessly. again, their risk of being into crashes, they've equalized that risk, but since they're driving faster, they're imposing additional risks onto you. Now I think about it, this probably has something I could have worked in with COVID here. But anyway, maybe another lecture. So when we think more generally, there's an evolution of human behavior that's going on. Decision-making and cognitive processes that change in eras of rapidly changing vehicle technologies. Now, I've probably in the last 5 to 10 years, I've looked at a lot of data on vehicle accident, lots of vehicle accident data. And almost invariably, what we find is this notion of temporal instability, which I'll talk about briefly in a second, is that so many things are changing because of car technologies and everything, that the behaviors that we thought were constant, maybe in the 1990s and even the early 2000s, are changing almost from a year-to-year basis. And you can do statistical tests comparing like 2017 to 2018, and you can show statistically that the effect of variables in determining the severity of crashes are changing. And some of that is due to changing features in cars. The other one, there's also a lot of cognitive science that looks at the effect of macroeconomic conditions on risk taking. So for example, we find that during the Great Recession, the accident rates start going down. Then when the economy starts becoming good again, the accident rates start going up. So people's risk is sort of changing in a global way. And there's also evolving attitudes and behavior with safety. So the notion of temporal instability, and if you look on my resume, I've written many papers recently about this. There's a vast body of literature from psychology, neuroscience, and economics, and cognitive science. I should mention my daughter's getting a PhD in cognitive science, and other fields that suggest that this temporal element is a big problem, and it's something that we really haven't addressed thoroughly in the accident methods that we currently use. And temporal instability, when you think about it, it has profound implications for traditional statistical analysis and even machine learning, because the advantage of machine learning is that you can process large amounts of data in very short periods of time. But the fact that they're changing, the fact that the betas or the effective factors may be changing over time still presents a forecasting problem that may be in the shorter term. So that's that's sort of the background of the idea of offsetting behavior. And probably what I'd like you to think about is when, as you're starting to, drive home or, the next time you get in a car, start thinking about the things and how your driving behavior has possibly changed in recent years. I know, and again, since I have the cars from different eras, it's very obvious to me that in addition to what might be changing with me overall cognitively and so on over time, I find my behavior changes dramatically from one vehicle to the next. So let me stop sharing and see where everybody is. So everybody's in good shape? I think we're like 45 minutes in, yeah.
Fred, you want to open for questions now?
Sure.
Yeah, so there's a question submitted through the Q&A box. So let me read it to you. So this question is related to Winston's paper published in 2006. And
yeah, which is that's
the
paper this is from. I was the co-author on it.
yeah, I think this is raised by Dr. Moyed Islam from your university, Carter Center.
Yes.
Yeah, his question is, if we would like to validate the empirical evidence with respect to the current automated advanced systems, such as automated driving system or advanced driving assistance system, do you tend to believe such advanced systems in automobile industry could help even risky drivers not to drive tailgating or engage in aggressive maneuvers such as lane change even though the non-random sample still exists?
Okay, so first I want to thank Muad, I think is in Orlando today. So it's not like we planted this question. But Muad and I have co-authored numerous papers together. We started to think about things like this, and we actually have a paper that is doing in the second round of review that looks at drivers that fall asleep in fatigue. So here's the bottom line, and again, you can think about this, is that as the safety features become more and more advanced, eventually we're moving to like a fully automated vehicle, right? So you have autonomous vehicles, but we're sort of in this interim phase where it is possible that the safety features can be offset. At some point, our safety features will become so advanced that they won't be able to behaviorally be offset. And I think we might be just like 5 or 10 years away from that, where the automated safety features in the cars will be sophisticated enough that they'll be able to respond to that. So for example, you may have eye tracking that will detect if you're starting to drive distracted, and it'll give you a warning. And if you don't heed the warning, then the autonomous part of the vehicle will take over, and then you'll just be, you won't be allowed to drive, and the car will drive itself for a while. So that is where I think the field is going, is that the safety features are going to start advancing so quickly that we're going to be able to overcome the risk compensation element. So my guess is that the risk compensation argument may only be sort of an important concern in the next 5 years to 10 years. And I think after 10 years, the vehicles will be sophisticated enough that they'll be able to overcome, they said at the end of the Good Morning America, be able to overcome the drivers, the human element. And when you think about what makes transportation such a difficult area of civil engineering, is we have humans, right? So we have to design a system for a human. When you do structures, you design for earthquakes, but you don't have humans. So it makes it a bigger challenge. It makes the transportation a bigger challenge. But at some point, we will have vehicles that are sophisticated enough that will be able to overcome any sort of human behavior that could have a deleterious effect on safety.
Thanks, Fred. So this question also have a second part, which
Okay.
will follow up with that, the same paper, figure 1.
Okay.
The trade-off between risky driving with speed adaptation can be compensated in a better way with ADS and ADAS for younger or older population groups, for passenger vehicles to trucks on roads relative to airbags and anti-lock braking.
So that's a good point, is that all of and it's not just airbags and anti-lock brakes, all the safety features have a different effect on different age groups. Now, when we estimate statistical models, we often use age, gender, and things like that as proxies for what is actually going on with the individual behavior. So it is possible that airbags, anti-lock brakes, and so on may be more effective for some groups than others. Now, this also gets into mind there's been recent speculation that airbags are currently tend to be more favorable for men than for women. And I think there's a bill moving through Congress that is going to require car manufacturers to test different size car dummies and stuff to see the effectiveness of airbags. Now, one possible solution to that is it's not so much a gender thing, but it becomes on what becomes the standard body. But you can imagine at some point that we will have sensors in the car that will determine the height, size, and weight of the body, and maybe even the age of the driver, and would adjust perhaps the positioning and acceleration of the airbags to be tailored to the occupant. You can imagine that happening at some point. But certainly, Muad's second point there is that different groups of people with different risk-taking tendencies would be affected by the technologies differently.
Yeah, thanks, Fred. There's another question from Hao Yang at the University of Washington. He's asking, how does the perceived effectiveness of safety features by individuals affect the risks taken by drivers?
Now, that's a very good point, because if you recall that graph that I had that point E that had them going like, so that point E, which was way down on that graph, which means you drove like a maniac and really reduced your overall accident risk, or, reduce your probability of having an accident. That's a case where you could severely overestimate the effectiveness of your safety features. And this is a very delicate line, because vehicle manufacturers, tell you how effective these are. And if they give you the sense that it's extremely effective and you're doing this risk compensation, you're likely to overcompensate driving faster and actually reducing your probability of being safe. So that can cause some significant estimation issues. Now, what people actually do is, especially with the active safety features where you can see how quickly your car brakes or pick up the lane departure, after you're in one of the cars with the lane departure and stuff, you start adapting your behavior. And probably within about 100 miles, you have a pretty good sense of how effective that system is going to be in helping you avoid an accident. But that initial estimation, as the question sort of suggests, could be a real problem, because there is an adaptation period where, to determine exactly how effective the safety features in the car are. So it's a good point.
Thank you, Fred. One more question, actually, that's from Amy Stearns of USDOT. She's asking if you have any thoughts on whether training should be required for vehicles with more safety features.
And this sort of gets into the previous question, because, if you did have a training period, that would help you get a more precise estimate of what, how effective these things are. Now, I should tell you my own experience. In the early 2000s, I bought a Mercedes, and then I went to this AMG experience, which is, you go on a racetrack with all of these Mercedes, and you start driving like really fast. And what I took away from that course is I could be driving a lot faster than I thought I could. So there is an advantage to being required to know how the safety features work, but you don't want to make it seem that the safety features will save you. So if you are required to have training on that, it has to be very carefully constructed so that you don't have people overestimate how safe their cars are. But I think that would be an excellent idea, although, and especially as the safety features become more and more advanced. I mean, you have to know when the autonomous braking is going to kick in. And a lot of times when they do this on a track or something, they'll have some cardboard thing, and you'll sort of approach it at a certain speed, and then the car will automatically stop. But knowing what those safety features could do could give you a better estimate on the probability of a crash. But it could also make you a more aggressive driver, because if you know it, it's like, wow, I was on the track and I know I can drive 50 miles an hour up to 100 feet away and it'll stop by itself. So then you may become more reckless that way, as opposed to having it, having it in reserve and not knowing how effective it is might be the safer alternative. But this could be an incredible study in cognitive science to see how you can sort of game the human behavior and trade it off against, the physical characteristics of the safety feature.
Okay, Fred, there's a question from a student in my 327 class, a junior student. He's asking, he said, I found the point you made on externalities very interesting. Do you think there are ways to mitigate the externalities imposed on pedestrians, motorcyclists, and cyclists, etc.?
So that's a very good point. I think the best way to do is probably to increase the safety features, so you can have pedestrian detection safety features. A lot of it, you could have like, infrared sensors that pick up pedestrians at night. So I think the way you can't have pedestrians walk around with like full body armor, or expect all the motorcyclists to have, body armor in their motorcycle suits and all of that stuff. So it's unrealistic to put the burden of protection on the vulnerable road users. So I think what's really needed is, really advanced safety features that can eliminate the impacts of the, potential offsetting behavior. So this is a very strong case for, pedestrian detection, really advanced pedestrian protection systems. And, when you think about pedestrians, I recently did a study that looked at the differences between day and night pedestrian crashes. And pedestrians, when you are a pedestrian, especially at night, you can see the headlights of the car, and your natural assumption is that they can see you. But when you're driving in a car, it's real easy to see the headlights of the car, but it's really difficult for the car to actually detect the pedestrian at night. So even though you're in their headlight field, it's very hard to pick up pedestrians. But you can imagine with infrared and other technologies, especially at night, you could make pedestrian safety much more effective. So the key there, I would say, has to be technologies in the vehicles that have to work on that.
Thank you, Fred. There are several more questions. I know we don't have a lot of time left there.
Oh, no, I see Linda.
You go, like 5 minutes, beyond the time we scheduled. Is that okay?
Okay.
Okay.
I see Linda Boyle has a question.
Yeah, but she needs to wait. There's more people.
Oh, okay. Yeah, I'm just looking down the list.
Yeah, so the next one is from Wei Zhang. And the question is, do you think the effect of stability control has more to do with increase in driver aggressiveness? This is the thing that driver can easily feel than the presence of airbag and ABS.
Yeah, because again, the stability control, I'm thinking one of my cars, the early 2000 is a Mercedes AMG, and it has a traction control that is amazing because it allows you to go off a street light from 0 to 60 in like 4.2 seconds. But if you take that traction control off, your tires start squeaking, you get a lot more feedback. And so your point with the stability control, and I should tell you, my cousin also races this Mercedes SLK 32s, and he was at a racetrack in mid-Ohio, and he turned off the electronic stability package, and he like spun out in the next corner. There's all kinds of things that go on that you just don't realize, but you're right in that those active safety features, you can instantly. Sometimes you don't realize all the corrections that are being made by the computer to keep you on the road. But if you take it off, you would realize it in a hurry. And one of the drills that we did at this Mercedes AMG course is we shut off the electronic stability control and went around a wet track and then turned it on. And it's a night and day difference. So that is a good point. I think the point that you're getting at there is the active safety features you can feel more versus the passive ones. It's like, oh, I have airbags on my knees and everywhere else, but you don't get that instant feedback that an active safety feature would give you.
Thank you, Fred. The next question is from Professor Mike Lowry of the University of Idaho. His question is, have you considered adding a chapter on safety in a later edition of your undergraduate textbook?
That's an interesting.
Yeah.
Now, unfortunately, I'm not the biggest fan of the highway safety manual, but the highway safety manual, I think, has great benefits. So especially if I do this at the undergraduate course, it would have to be based on the highway safety manual, and then all of the research that I do sort of says why you shouldn't use the highway safety manual. So I would have some sort of moral dilemma there. But it's, I should tell you, the highway safety manual is excellent for what it does. But if you look at like the frontline accident research that starts thinking about all this risk compensation and other stuff, the models become incredibly more complex than those that are in the highway safety manual. But you can see where the highway safety manual is likely to go like 10 or 15 years down the road. So I'll have to, maybe if Mike, if you would like to be a co-author on that chapter, that, we could talk about that because, I have like this moral, I've never, the highway safety manual, I'm like, it's great, but here's how you should do it if you did it right. But it's not, I totally understand the highway safety manual is an extremely valuable tool. And perhaps at some point, that could be a chapter in the book. So, but I'm not sure I'm the person to write that because as soon as I start talking about safety, I'm start thinking about offsetting behavioral, temporal instability, all of these things that are not going to be on a fundamental exam, right? They're not going to be on the FE exam. So, but yeah, we can talk about it if you want to be a co-author.
Linda cannot wait for longer. This is Linda's turn. Her question is with regard to your comments that risk compensation may go away in 5 to 10 years. It is not clear that will be the case. While the automation may continually improve, it is still not perfect. And humans will continue to adapt to the limitations to the technology as the technology keeps learning about limitations in humans. Hence, there is a circular compensation that is going on. Any thoughts?
Yeah, no, Linda, that's an excellent point. And I can see you're making a case for you're continuing to do research on human factors. So, but no, that's an excellent point. I think there's, as the technology starts rapidly moving forward in 5 to 10 years, I think we'll start be able to, the effect of human factors may become less because we'll be able to compensate for the offsetting behavior. But Linda brings up a good point, is that you should never underestimate how humans can neutralize anything that you do with that involves engineering. And so I totally agree that until you take the human completely out of the system, they're going to find some way to mess things up.
Yeah, there are 3 more questions, Fred. Do you want to finish them or you want to stop here?
I'm fine. It looks like we have some of my Australian colleagues are starting to chime in. I could, well, you do the time.
Yeah, okay, let's finish this then. The next question is from Shimo Heck. The question is, thanks for the great presentation, Professor. Over the years, we are also having more in-vehicle distraction activities. How can we control this factor in the econometric model in order to estimate the safety benefits of advanced vehicle features?
Well, yeah, that's a really complex problem, and requires very large amounts of data, controlled experiments. Yeah, to be honest, that's something that we should write a paper together in AMAR to sort of maybe set up sort of a foundation of how you might develop experiments to deal with that. But that's it's a very good question, but it's a very difficult problem and a very difficult problem to address, in a few minutes. But I mean, that would be an excellent possibility for writing a paper.
Okay, the next question.
You can imagine the econometrics could become amazingly complex.
The next question is from Shams. Yasmin.
Yeah, we just Shams.
Okay, sorry. How is it possible to deal with the complexity of having several safety features in a vehicle, while some vehicles has minimal number of safety features? In Australia, passenger vehicle fleet is 12 years old. which makes it even challenging.
Mm-hmm. Yeah, that's an interesting problem. And you know, a lot of people, I'll give sort of an anecdotal thing. I have a sport bike that it's a 2002. So it doesn't, if you look at a modern day sport bike, you know, motorcycle sport bike, they have traction control, anti-lock brakes, suspension adjusts itself. And I have this early 2000, it's like the last fast model that doesn't have anything, any adjustment. So this, you know, this period of having a great mix, you know, because even in the United States, the average age of the car is 10, 12 years old. Almost every car now has airbags, but there are very few cars, and, you know, probably more than half the fleet has side impact airbags. But when you start getting into more advanced safety features, it's really a small portion of, and you know, this gets into the whole issue of the people in the more advanced safety features cars putting externalities on people that are not in those advanced safety cars. So it's a real problem. And again, that's something, you know, Shams, we can maybe write a paper on that too. But a lot of paper ideas with this. But yeah, I'm not sure I could give an exact answer. But one of the problems of advanced safety features is the mix of cars on the road. So if somebody has advanced safety features and somebody doesn't, then a lot of externalities and equities could become a problem.
Okay, so Fred, now the last question we should answer. This is from Christopher Brandon. Do you think the fact that the speedometers show a higher range than older cars contribute to faster driving? I remember my 1986 Buick LeSabre had a top speed of 85, but now Toyota Corolla and other smaller vehicles have 130 as a top speed.
Yeah, that's an interesting, very interesting point, because I remember those days where it was probably in the mid 80s where every car could not have a speedometer go above 85. That is an interesting. I'm not aware of much research that has been done on that. Whether that having that the speedometer maximum of 85 actually had an effect on high speed crashes or not. But I notice, I have one car that speedometer goes to 180, but it's electronically controlled at 155. But I have to wonder, I don't think too many people probably exceed 100 a lot. But, there was a time in Montana when there was no speed limit, right? And I always tell this story. I had a Infiniti Q45 and the speed, there's no speed limit. So I took it back to the dealer and said, the speed, the cruise control doesn't set above 100 miles an hour. So he said, well, this is not something we can test in the shop. But they found out it was actually a safety feature that the cruise control would not set above 100. But you have to think, people think when you're, 100 miles an hour, that's ridiculous. If you ever drove in the plains of Montana, it's amazing. And this is true from my experience in racing and so on, is once you start going 100, now this is on a racetrack. I don't do this on the road. So once you start going 130, 140, everything starts slowing down. And when you go to 70 miles an hour, it feels like you're going 10 miles an hour or something. So your mind does start adjusting to that. And, as long as you're not into heavy traffic and stuff like that, that could, but it would be fascinating. There were two elements I would be interested in knowing. What were the effect of those 85 mile an hour speedometers on cars? Because I think there was like a 5-year period or so that they were required to have 85. And then also, what happened in Montana when there was, no speed limit? And I can remember driving there when there was no speed limit. I would usually drive like 90, and there were other cars driving at 92, right? Even though I passed the cop up going 90, and the cop was going like 89 or something. It's very slow and safe. But I noticed that over time, in going back to Montana, in subsequent years, everybody started slowing down. So I think they started gathering information. Now I should say, although Montana had no speed limit, that was at daytime. The nighttime speed was 65 miles an hour because, you know, in the daytime, you could drive off you fall asleep, drive off the road for half an hour and get back on. But at night, you start hitting deer and stuff. So at night, it was 65 miles an hour.
Right, actually, I just noticed Steve Burgess also asked a question in the chat box. I think I have the pressure to ask you to answer that question. The question is, how have changes on traffic law enforcement with time influenced your findings?
Now that's a good point too, because it's quite interesting. When the speed limit was 55, if you remember the last energy crisis, well, none of you will remember, but it was in the 70s. Everybody put in the national 55 mile an hour speed limit. But what happened is that the federal government required a compliance to that 55 mile an hour speed limit. So they put a lot of law enforcement on the roads that were 55, and those happened to be the safest roads because interstates are the safest road. So one of my colleagues has argued that the 55 mile an hour speed limit and the allocation of law enforcement resources to that road actually increased the accident rates because they should have been patrolling the roads that had slower speeds that were more dangerous than in enforcing the 55 mile an hour road on a road that would be safe at 70 miles an hour. But you know, Steve's point's well taken, is that how people enforce the speed limit is quite interesting. And there's a section of Interstate 80 called the Borman Expressway, just south of Chicago. And it's the most heavily traveled truck road in America. And I had a state patrol talk to me once, and he said, you can drive as fast as you can on that road because we'll never pull anyone over because it's too dangerous. You know, there's no place to pull over. There's so many trucks. And so Steve's point is well taken. It would be interesting to study how enforcement is a very tenuous thing, you know, how effective it is in reducing crashes. And, but it's also interesting how police allocate their resources to enforce speed. I think the assumption, my impression here in Florida, is that they tend to assume that the drivers will self-regulate. Although there have been studies in COVID, you've probably seen that during COVID with less congestion, you're starting to get very high tickets, you know, people getting a ticket going 120 in a 70 mile an hour zone.
Right, so I know there will be more questions. Actually, there's still questions unanswered. I also have several questions, but I will wait until you come to Seattle in the fall. Okay. For the audience still online, so PacTrans is going to organize our region week of October. I hope you can join us. And Dr. Manning already committed to the conference, so hopefully you can talk to him in person in the fall.
Yes.
With that, Fred, so thank you so much for your excellent presentation and your discussion with our audience. We certainly look forward to your visit in the autumn, and thanks a lot and have a nice day.
All right, thank
everyone.
you. Take care, everyone.